that we reviewed Newton's first three laws, Law 1, inertia, Law 2, F equals ma, Law 3, action-reaction pairs, we can use those laws and those ideas to help us quantify situations where there's multiple forces acting on an object, and then predict if that object is accelerating or if it's has a zero acceleration or a constant velocity. It might be at rest, it might be moving a constant speed in one particular direction, but we can use those three laws to help us determine what is happening to the object. There are 5 steps basically to solving these problems. Of course, draw a picture that's kind of to scale with all of the forces acting on the object. We don't care about what caused the forces exactly, we just care about what the forces acting on the object are. Then identify all the known and the unknown values. We have done this a lot with other types of problems. We've written down all of the values in the problem. If any of the forces are acting in both the x and the y dimension, we must resolve them into their x and their y components. The next step then is to find the net force in each direction, so put all your x's together and all your y's together, and then the final step, find the resultant or the overall net force acting on the object. Remember that net force is a vector, and so you must have direction and magnitude to completely answer the question. So here's a practice problem that we could work on. So Joe leaves his physics book on top of a table. It is inclined at 35 degrees. The free body diagram is shown at the left, and we want to find the net force acting on the book. In this picture, they kind of did the first 2 steps for you, which is draw a picture to scale and then identify all the known and unknown forces. They gave us the gravity or the weight force acting on the book as 22. They gave us the normal force acting on the book, and notice that's the table pushing out on the book at an angle. That's at 18 newtons. And then friction is up the incline because the book has a tendency to slide down the incline. Friction will be opposite that motion, and so 11 newtons of force up the incline. We are going to find the net force. Now, obviously, if you look at this, I can't just add all these forces together because they're not all in the same dimension. So this is the picture. I'm going to kind of simplify the picture just a bit so we don't have all the extra information on there. And I'm going to add, I can't draw very straight here, the angle that they indicated in the problem, 35 degrees. Now, here's the tip right here. To simplify the problem, always choose the coordinate system, which gives you as many forces as possible in the x and y axis. If I use a traditional axis system, like this, y, and x, you can see that the 18 newtons and the 11 newtons would be in both x and y, and the 22 newtons would be the only one in the y-axis. So I would have to resolve both the 18 and the 11. If I choose a non-traditional x and y axis system, which is indicated on the page here, on the screen, where the incline is my x and perpendicular to the incline is my y, then the only one that I need to resolve into its components is the 22 Newton force. So we kind of talked about this, I don't know, a few days ago when we were just drawing pictures, that if I want to resolve this 22 Newton force into its 2 components, I want to figure out, well, how much in the y, so that's along the y-axis, and then how much in the x, along the x-axis, is that force acting. So there's my y and there's my x. Make sure that your x and your y are a 90-degree angle to each other, and that your x is parallel to your incline. Mine is not perfect, but it should be right along that incline ramp. Now, a little bit of geometry review, or even just trig triangle review, is that if this is 35 degrees, and I have this triangle right here, like so, if I know this is 35 and this is a 90-degree angle, I know this one right here is 55 degrees, because 35 and 55 add up to 90. Well, then what is this angle inside of here? Well, looking at my y and my x, they must be 90 degrees to each other. So this one right here must also be 35 degrees. That will always work. So if your angle with the incline is 35 degrees, that was even messier, then the angle inside must also be 35 degrees. So here is my y, and here is my x. And so now I know a hypotenuse and an angle, and so I can find the two sides. So I take, and I've said this multiple times, if you don't know anything else to do, if you have an angle and a hypotenuse, you can just find the two sides. So sine of 35 is the opposite over the hypotenuse, 22. And you'll find that x is equal to 12.6187. Do not round this answer because this is not my final answer. This will also be in newtons because we're resolving a force vector. And then we'll do cosine of 35 is the y over 22. And so the y component is 18.021. So my x I have here is basically 12.6. And my y is into the ramp 18.0. The next step in the process, as the steps said, was to find the net force in each direction, or find the sum in each direction. So I want to look at my picture and see, well, how many forces do I have acting in the x direction? I have the normal force, 18 newtons, pointing out of the incline, and I have the y component of the weight force into the board. So my total in y with sig figs, because now I'm adding and subtracting, this has no digits to the right of the decimal, this one has 1. And so my answer is going to be 0 in the y direction. This makes sense because my book is not accelerating in the y direction. It would be a little bit unusual if the book started like levitating off the table or falling into the table in the y direction. The total in the x direction then is 12.6187 minus, because that's down the ramp, minus 11, which is up the ramp. And so that will leave me with a 1.6. Again, not my final answer here, 1.6 newtons in the x direction. And so the last step is find the net force acting on the object. Well, if it's 0 in the y and 1.6 in the x, then the net force is only in the x direction, and it's going to be down the ramp. So this book is going to have a net force of 2 newtons in the positive x direction. And therefore, the book is going to accelerate down the ramp. It's not going to be at rest on the table. It's going to be going faster and faster down the table. The possible follow-up question to this is, well, what is the acceleration of the book down the ramp? Well, we can find the acceleration if we know the mass and the net force. Well, we know the net force is 1.6. I rounded it to 2 for sig figs, but now if I'm going to go another step to find acceleration, I'm going to go back to the 1.6. The mass was not directly given in the problem. They gave me the weight force of the book, and so I'm going to have to find the mass by taking the 22 Newton weight force and divide by 9.81 to get the mass of the book, which ends up being, when you divide that out, 2.24 kilograms. So I take this mass, plug it in there, and then solve for the acceleration. That's a 4. And when you solve for the acceleration, you get 0.72 meters per second squared, which could round to 0.7 with 1 sig fig. So that is the process that you use to solve those equilibrium type problems.